13 billion miles from the warmth of your skin. A machine no larger than a compact car drifts through darkness so absolute that light itself seems to hesitate before crossing it. It has been falling forward since 1977, long before you were born, long before the world you know took shape. Carrying a golden record etched with the sound of thunder, the laughter of children, and a mother's heartbeat pressed into grooves of copper and gold. No human hand will ever touch it again. No human eye will ever see it tumble through the black. Yet somewhere out there, at the bleeding edge of everything our star can reach, this ancient traveler struck a wall that should not exist, detected a hum that should not sound, and measured temperatures that rise where every equation promised cold. The solar system you thought you knew has a border, and that border is alive, breathing, rippling, pushing back against the void with a fury no one predicted. What Voyager found at the edge of our cosmic neighborhood does not simply challenge textbooks. It reshapes the meaning of home itself. If this channel helps you see the universe differently, a like and subscribe means more than you know. It is what keeps these journeys alive. Prepare for a journey through the outermost silence beyond comprehension. We begin. There is a window in the sky that opens once every 175 years. Not a window you can see with your eyes, not a gap in the clouds or a break in the atmosphere. It is a window of geometry, a rare moment when Jupiter, Saturn, Uranus, and Neptune line up in such a way that a single spacecraft can visit them all, one by one, using nothing but gravity to sling itself from world to world. No engine powerful enough exists to carry enough fuel for such a journey, but gravity is free. And in 1977, that window cracked open. NASA knew this was their only chance, not for a decade, not for a century, for 175 years. The next alignment would not come until the year 2152. Engineers who were young men and women in 1977 would be dust long before that window opened again. So they built two machines, Voyager 1 and Voyager 2. Twin spacecraft, each about the size of a small car, wrapped in aluminum and gold foil, bristling with antennas and instrument booms. They weighed less than a ton each. They carried cameras, magnetometers, plasma sensors, cosmic ray detectors, and something no other spacecraft had ever carried before. A golden record. Picture it. A 12-inch disc made of copper, plated in gold. On its surface, grooves spiraled inward like a vinyl record from your grandparents' living room. But this record did not carry pop songs or jazz standards alone. It carried the sound of Earth, thunder rolling across plains, wind moving through trees, waves crashing on a shore no alien has ever visited, a baby crying for the first time, greetings spoken in 55 languages from ancient Sumerian to modern Mandarin, music from every corner of humanity. Beethoven's Fifth Symphony, Chuck Berry's Johnny B. Good, a Navajo night chant, Japanese shakuhachi flute, Peruvian panpipes, Pygmy initiation songs from Zaire. Each piece chosen to say something about who we are. 116 images were encoded on the disc, diagrams showing how to decode them, mathematical definitions so that any intelligent species could reconstruct the pictures. And what would they see if they did? DNA structure, human anatomy, animals and landscapes, cities and buildings, a woman nursing a child, a family eating dinner, the diversity of life on a pale blue world orbiting an ordinary star. The cover of the record carried instructions etched in metal. How to play it, what speed to spin it, how to convert the encoded data into images, and a map. 14 pulsars, neutron stars that flash with clockwork regularity, drawn with lines pointing back to our sun. A cosmic return address. If anyone ever found the record millions of years from now, they could triangulate Earth's location by measuring pulsar frequencies. Then, President Jimmy Carter included a message. It read in part, "We are attempting to survive our time so we may live into yours." That line hits differently now than it did in 1977. Back then, nuclear war threatened everything. Climate change was barely a whisper. The message was hopeful and terrified at the same time. We sent our voice into the dark because we were not sure we would last long enough to send it again. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed 16 days later on September 5th. Despite launching second, Voyager 1 traveled on a faster trajectory. It reached Jupiter first in March 1979. The images it sent back changed everything we thought we knew about the giant planet. Volcanic eruptions on Io, Jupiter's closest large moon. Rivers of sulfur pouring across a tortured surface. No one had predicted active volcanoes on a moon that small. Then onward, to Saturn. The rings revealed themselves not as smooth bands, but as thousands of individual ringlets, braided and twisted by shepherd moons no one knew existed. Voyager 2 took a longer route. It visited Jupiter 2, then Saturn, then continued to Uranus in 1986 and Neptune in 1989. It remains the only spacecraft to have visited those distant ice giants. The photographs of Neptune's great dark spot, a storm the size of Earth swirling in an atmosphere of methane and hydrogen, were among the most beautiful images ever taken by a machine. After Neptune, the planetary mission ended. The cameras were turned off. There was nothing left to photograph. Both spacecraft were now heading outward, away from the sun, away from every world they had visited, into a region no human-made object had ever entered. Mission planners gave them a new assignment: keep flying, keep measuring, tell us what lies beyond the planets. Nobody expected them to last. The engineers had designed systems to survive 5 years, maybe 12 if they were lucky. The instruments were built with 1970s technology: vacuum tubes in some circuits, hand-soldered transistors, magnetic tape for data storage. The onboard computer carried 68 kilobytes of memory. Your phone carries billions. Yet these machines kept working, year after year, decade after decade, through temperature swings from boiling radiation near Jupiter to the creeping cold of deep space where thermometers read minus 270 degrees. By the early 2000s, both Voyagers had traveled farther than any object humanity had ever built. They were approaching a region scientists called the termination shock, the place where the solar wind, that million-mile-per-hour stream of charged particles flowing outward from our star, begins to slow down. Something out there was resisting it. Something was pushing back. And the instruments that were only supposed to last 5 years were about to detect things that would rewrite our understanding of where our solar system ends and where the universe begins. The golden record spins silently in its protective cover. The cameras are dark. The tape recorders are off. But the plasma sensors still listen. The magnetometers still feel the invisible architecture of space. And the cosmic ray detectors still count particles that have traveled across the galaxy to strike a machine no bigger than a dining table. Voyager is old. It is tired. Its power fades by 4 watts every year as the plutonium in its generators slowly decays. But it is still alive, still transmitting, still whispering across 13 billion miles of darkness. And what it whispers back has changed everything. The distance is almost impossible to hold in your mind. 13 billion miles. If you drove a car at highway speed without stopping, it would take you more than 25 million years to reach Voyager 1. Light itself, the fastest thing in the universe, takes over 21 hours to make the trip. When mission controllers on Earth receive data from Voyager, they are looking at the past. Events that happened yesterday arrive today. Commands sent today will not reach the spacecraft until tomorrow. The round-trip delay is 42 hours, nearly 2 full days of silence between question and answer. Yet through that silence, data still flows, 160 bits per second, slower than the earliest dial-up internet connections from the 1980s. A whisper so faint that only the largest radio antennas on Earth can hear it. 3 stations spread across the planet: Goldstone in California, Madrid in Spain, Canberra in Australia. Together they listen around the clock, passing the signal from one dish to the next as Earth rotates, never losing contact, never missing a word. And the words Voyager sends are extraordinary. The solar wind is invisible. You cannot feel it on your skin or see it with your eyes, but it is real, and it is violent. Every second, our star throws millions of tons of charged particles outward into space. Protons and electrons ripped from the sun's atmosphere, accelerated to speeds of 1 million miles per hour. This wind does not blow gently. It screams outward in every direction, filling the space between planets, pushing against everything it meets. It is the breath of our star, and it reaches far beyond the last planet. For decades, scientists believed this breath would fade slowly. Like a river widening as it approaches the sea, the solar wind would thin out, weaken gradually, and eventually blend into the quiet of interstellar space. A smooth transition, a gentle ending. The math supported this idea. The models looked clean. Everything pointed toward a slow, predictable decline. Voyager 1 reached the termination shock in December 2004 at a distance of 94 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to our star, about 93 million miles, so Voyager was roughly 8.7 billion miles out. This is where scientists expected the solar wind to begin slowing down. The place where our star's influence first meets serious resistance from the material between the stars. What the instruments detected was nothing like the models predicted. The solar wind did not weaken gradually. It stuttered. Speed dropped suddenly, then surged back, then dropped again. Over weeks and months, the pattern repeated in wild, unpredictable waves. The instruments recorded fluctuations that looked like something was pushing back against the wind, not steadily, but in pulses, as if the boundary between our solar system and the outside universe was breathing, expanding when the sun pushed harder, contracting when the sun grew quiet. Think of it like a river meeting the ocean. The fresh water pushes forward, but the tide pushes back. Sometimes the river wins, sometimes the ocean wins. The boundary between them shifts with every wave. That is what Voyager was flying through, a cosmic shoreline where 2 vast forces collide, and neither one wins completely. Then, the cosmic ray detectors started behaving strangely. Cosmic rays are particles from outside our solar system. They come from exploding stars, colliding galaxies, and violent events scattered across the universe. These particles travel at nearly the speed of light, carrying enormous energy. Normally, the solar wind and the sun's magnetic field act like a shield, deflecting most cosmic rays away from the inner solar system. This is one reason life survives on Earth. The shield keeps the worst radiation out. Scientists expected cosmic ray levels to rise smoothly as Voyager traveled farther from the Sun. Farther from the shield means less protection, more cosmic rays getting through. Simple logic, but the data told a different story. Cosmic ray counts spiked suddenly. Then they fell. Then they spiked higher than before. The pattern was not smooth at all. It looked like a staircase. Sharp jumps separated by flat plateaus. Each jump corresponded to Voyager entering a slightly different region of space with different shielding properties. Something was blocking the cosmic rays in layers, then letting them through, then blocking them again. An invisible barrier appeared and disappeared like a wall made of mist. Engineers at NASA checked the instruments carefully. After 27 years in space, any sensor could malfunction. Radiation damage, temperature stress, component aging. All of these could produce false readings. But every cross-check came back clean. The instruments were working perfectly. The readings were real. Something genuinely strange was happening at the edge of our solar system. Mission scientists began building a new picture. The termination shock was not a clean line drawn across space. It was a living, moving zone. The Sun's activity follows an 11-year cycle. During peak activity, sunspots multiply, solar flares erupt more frequently, and the solar wind blows harder. This stronger wind pushes the termination shock farther outward. During quiet periods, the wind weakens, and the shock contracts inward. The boundary moves by billions of miles depending on what the Sun is doing at any given moment. Voyager was flying through a zone that refused to sit still, like trying to cross a doorway that keeps sliding left and right. Sometimes Voyager was inside the shock. Sometimes it was outside. Sometimes it was caught right in the middle, where conditions changed hour by hour. But even this explanation left puzzles. The magnetic field readings showed something nobody could account for. As Voyager crossed the termination shock, the magnetic field lines should have started shifting direction. Inside the heliosphere, the Sun's magnetic field dominates. The field lines spiral outward, twisted by the Sun's rotation like water from a spinning sprinkler. Beyond the shock, those field lines should begin giving way to the interstellar magnetic field, which comes from a completely different direction based on galactic structure. But the field lines barely changed. They stayed mostly the same orientation on both sides of the shock. It was like walking through a doorway, expecting a new room and finding the same furniture arranged in the same way. The magnetic signature of our Sun persisted far beyond where anyone expected it to reach. This created a problem for every existing model of the heliosphere. If the magnetic field did not change at the termination shock, then where did the Sun's influence actually end? How far does our star's magnetic fingerprint extend into the darkness? And what force was strong enough to slow the solar wind to a crawl while leaving the magnetic field untouched? Voyager 2 provided a crucial comparison. It reached the termination shock in August 2007, 3 years after its twin, but it crossed at a different distance, only 84 astronomical units from the Sun, 10 astronomical units closer than Voyager 1. That difference represents nearly 1 billion miles, a gap so large that no model had predicted it. The two spacecraft crossed the same boundary at vastly different distances, proving the termination shock is not symmetric. It is lopsided, shaped by forces no one had properly accounted for. The interstellar medium pushes harder on one side of the heliosphere than the other. Our solar system moves through the galaxy at 43,000 miles per hour. The side facing our direction of travel gets compressed. The opposite side stretches outward. Voyager 1 flew through the compressed nose. Voyager 2 flew through a region closer to the stretched flank. Same boundary, different distances, different conditions. The termination shock was supposed to be simple. A line in the sand where the solar wind slows down. Instead, a Voyager found a heaving, shifting, asymmetric zone that pulses with the heartbeat of our star. And beyond that zone, something stranger waited. A region no scientist had ever imagined. A corridor between two worlds that existed in no model and appeared on no map. Voyager was about to enter the highway. The data continued streaming back at 160 bits per second. Each packet took hours to compile and transmit. Each packet crossed billions of miles of empty space before reaching the massive dish antennas on Earth. Scientists studied every number, every fluctuation, every spike in the readings. They argued in conference rooms and published competing papers in journals. Some believed the termination shock was a temporary feature that would smooth out over time. Others believed it revealed permanent structure in the heliosphere that no previous theory had captured. What everyone agreed on was this: the edge of our solar system was far more complex, far more dynamic, and far more violent than anyone had imagined. And Voyager had only reached the first boundary. The true border still lay ahead, hidden somewhere in the dark, waiting to be crossed. Beyond the termination shock, Voyager entered territory that existed on no map. Every model of the heliosphere showed a simple picture. Inside, the solar wind dominates. Outside, interstellar space begins. Two zones. One boundary. Clean and straightforward. But Voyager discovered a third region hiding between them. A place where the rules of both environments blurred and merged into something entirely new. In 2009, Voyager 1 detected something that made mission scientists stop and stare at their screens. The solar wind, which had been slowing for years, dropped to zero. Not gradually over weeks or months. Within a few days, the outward flow simply stopped. The stream of charged particles that had been blowing past the spacecraft for over 3 decades went silent. Yet Voyager was still inside the heliosphere. It had not yet crossed into interstellar space, but the wind that defined our star's influence had vanished. What replaced it was movement in a direction no one expected. Particles began flowing sideways, not outward from the sun, not inward from the stars, sideways, parallel to the boundary between solar and interstellar space. Charged particles from both environments traveled along the same corridor, flowing in both directions simultaneously. Solar particles moved one way, interstellar particles moved the other. They shared the same road. Scientists named it the magnetic highway, a corridor of magnetic field lines that connected the inside of the heliosphere to the outside. These field lines acted like rails on a track, guiding particles along their length while preventing movement across them. Imagine two rivers running side by side in opposite directions, separated by nothing but an invisible current. The water on each side knows where to go, but they share the same channel. This region was never predicted, not by any computer simulation, not by any mathematical model, not by any theoretical paper published in the decades before Voyager arrived. The magnetic highway was a complete surprise. It revealed that the transition from solar to interstellar space is not a single step, but a journey through a buffer zone where two cosmic environments mix, compete, and coexist in uneasy balance. The magnetic field measurements inside this highway deepened the mystery. The field lines remained oriented in the same direction they had pointed throughout the heliosphere. Solar magnetic field geometry persisted even in this strange corridor. If Voyager had truly entered a transition zone, the field should have begun rotating toward the interstellar direction. It did not. The sun's magnetic fingerprint clung to this region stubbornly, refusing to let go, but the particle data told a completely different story. Cosmic ray counts jumped sharply when Voyager entered the highway. These high-energy particles from outside the solar system suddenly had access. The highway let them in. At the same time, lower-energy solar particles began dropping away. They were escaping outward along the same corridor. The magnetic highway was acting like a two-way valve, letting interstellar particles pour in while letting solar particles leak out. This created a paradox. The magnetic field said Voyager was still inside the heliosphere. The particle data said it was touching the outside. Both measurements were accurate. Both instruments functioned perfectly. The spacecraft existed in two worlds at once, neither fully inside nor fully outside, suspended in a corridor that belonged to both environments and neither. Scientists debated fiercely. Some argued Voyager had crossed the heliopause, the true boundary of the heliosphere. They pointed to the cosmic ray surge as evidence. Others insisted the unchanged magnetic field proved Voyager remained inside. The debate played out in journals, at conferences, and in press rooms at NASA. Their headlines swung back and forth. Had Voyager left the solar system or not? The answer was neither. Voyager occupied a zone that nobody knew existed, a buffer between empires, a no man's land where solar and interstellar forces tangled together without either side winning. The highway stretched across a vast region, and Voyager spent years traveling through it. Years of ambiguous data. Years of arguments among the brightest minds in heliophysics. What made the highway even stranger was its behavior over time. The corridor did not remain steady. It fluctuated. Sometimes cosmic ray levels would surge, suggesting the highway had opened wider. Other times they would drop, suggesting it had narrowed or shifted. The highway seemed to respond to activity on the sun's surface. When a solar eruption sent a shockwave outward, the highway rippled. Particles scattered. The corridor temporarily closed, then reopened hours or days later. This responsiveness revealed something profound about the heliosphere's edge. It is not a wall. It is not even a membrane. It is a living, dynamic interface that reacts to events billions of miles away on the solar surface. A flare erupting on our star can shake the boundary of our solar system days later. The heliosphere is connected from core to edge by magnetic field lines that carry energy and information across unimaginable distances. Some researchers proposed a radical idea. Perhaps the magnetic highway is not unique to our solar system. Perhaps every star with a stellar wind creates a similar buffer zone at its boundary. If so, then every heliosphere in the galaxy has a highway. A corridor where stellar and interstellar particles mingle. These highways would form a vast network threading through the galaxy, connecting star systems through shared magnetic architecture. It is a speculative idea, untestable with current technology, but Voyager's discovery makes it plausible. The highway also raised questions about cosmic ray penetration into the heliosphere. If particles can flow freely along this corridor, then the heliosphere's shielding is not as simple as scientists believed. Cosmic rays do not just push through the boundary by brute force. They find corridors. They follow magnetic pathways. The shield has doors, and the magnetic highway is one of them. Again, this means Earth's cosmic ray exposure depends not just on how strong the solar wind is, but on how many corridors exist and where they point. For 3 years, Voyager traveled through this impossible region. 3 years of data that challenged every assumption about where our solar system ends. 3 years of particles flowing sideways while the magnetic field refused to change direction. 3 years in a corridor between worlds. Then, in August 2012, something shifted. The cosmic ray count did not just rise, it jumped. Solar particles did not just decrease, they collapsed. In a single day, the character of space around Voyager transformed completely. The magnetic highway had delivered the spacecraft to its final threshold, the outermost wall of our star's domain, the heliopause, and what waited on the other side would confirm that Voyager had done something no human creation had ever accomplished. It had left home, not just the neighborhood of planets, not just the reach of sunlight, but the entire bubble of influence our star blows into the darkness. Voyager stood at the doorstep of true interstellar space, surrounded by material that had never known the touch of our sun. And the readings it sent back from that doorstep were unlike anything recorded in the history of science. The corridor was behind it now. The unknown stretched ahead, and Voyager, old and fading, kept measuring. Temperature in space is a strange thing. There is no air to feel warm or cold, no breeze to chill your skin, no atmosphere to trap heat. Yet temperature exists everywhere in the universe because temperature is really just a measure of how fast particles move. Fast particles mean high temperature. Slow particles mean low temperature. Even in the emptiness between stars, the few particles that drift through the void carry energy. They move, they collide, and their speed tells us how hot or cold that region of space truly is. Inside the heliosphere, the solar wind carries particles at extraordinary speeds. Voyager's instruments measured plasma temperatures averaging around 100,000 degrees. That sounds terrifying. Hot enough to vaporize steel instantly. But here is the paradox. A human floating in this plasma would freeze to death in seconds. Heat requires density. You need enough particles hitting your skin to transfer energy. The solar wind is unimaginably thin, a few particles per cubic centimeter. So, despite the extreme temperature, there is almost no actual heat. The particles are fast but rare, like standing in a room where a single grain of sand flies past at bullet speed every few minutes. Technically dangerous, practically freezing. As Voyager moved beyond the termination shock and into the magnetic highway, scientists expected temperatures to drop. The logic seemed bulletproof. The solar wind was slowing down. Slower particles mean lower temperature. Basic physics taught in every university on Earth. The models agreed. Temperature should decrease as Voyager approached the heliopause, a gentle cooling toward the cold of interstellar space. The instruments told a completely different story. Temperatures climbed, not by small amounts, not by modest percentages that could be explained away as measurement error. In some readings, temperatures jumped to over 250,000 degrees, higher than anything recorded closer to the Sun, higher than any model predicted for this region. The numbers seemed impossible. The edge of the solar system was hotter than its interior. The science team erupted into debate. Some researchers suspected the instruments were failing. After nearly 4 decades in space, battered by radiation and subjected to temperature swings from boiling to near absolute zero, the sensors had every reason to malfunction. Circuits degrade, materials weaken. Components that worked perfectly at Jupiter might produce garbage data at the edge of the heliosphere. But cross-checking eliminated that theory. Multiple instruments on Voyager, one showed consistent readings. Different sensors measuring different properties all pointed to the same conclusion. The temperature was real. Then, Voyager 2, traveling through a completely different region of space billions of miles away, reported the same phenomenon. Higher temperatures near the boundary. 2 spacecraft with separate instruments on separate trajectories detecting the same impossible heat. The data was not wrong. and space was genuinely hotter where it should have been cooler. The explanation required physics that most people never encounter in everyday life. When the solar wind collides with the interstellar medium, the particles do not simply stop and settle. They compress, they pile up. Imagine a highway full of cars moving at 70 miles per hour suddenly hitting a wall of stopped traffic. The cars at the front slam to a halt. The cars behind crash into them. Kinetic energy has to go somewhere. On a highway, it becomes crumpled metal and broken glass. In space, it becomes heat. The boundary region of the heliosphere is a zone of extreme compression. Solar wind particles slam into interstellar material millions of times per second. Each collision converts motion into thermal energy. The plasma heats up. The boundary becomes a furnace created not by fire, but by friction on a cosmic scale. Particles that were flowing freely through the heliosphere suddenly find themselves squeezed into a shrinking space, and their energy has nowhere to go except into temperature. But compression alone could not explain temperatures reaching 250,000 degrees. Another process was at work, something more violent and more fundamental: magnetic reconnection. Picture two rubber bands stretched tight in opposite directions. Now imagine them crossing each other and suddenly snapping. The stored energy releases in an instant. That is magnetic reconnection. When magnetic field lines from different sources meet, they can cross, break, and reconnect in new configurations. Each reconnection event releases enormous energy, not gradually, not gently, in explosive bursts that heat the surrounding plasma to extreme temperatures. At the edge of our solar system, this happens constantly. The solar magnetic field pushes outward. The interstellar magnetic field pushes inward. Where they meet, field lines from both sides tangle together like threads from two different spools. They twist around each other. Tension builds, then they snap, energy releases, plasma heats, and the process begins again immediately. Voyager detected these reconnection events as temperature spikes. The readings would jump over hours, settle for a while, then spike again. Each burst was like a small explosion spread across millions of miles. These events also accelerated particles to incredible speeds, sending them racing in all directions. The boundary was not calm. It was a war zone of magnetic energy. The temperature readings also revealed something unexpected about what lay beyond. The interstellar medium itself was hotter than predicted. Scientists had calculated that the local interstellar cloud, the region of space our solar system currently moves through, should have a temperature around 13,000 degrees, warm by human standards, but far cooler than the boundary zone. Voyager confirmed this general range, but found the actual interstellar plasma running closer to 50,000 degrees, 5 times hotter than theory suggested. Something was heating the space between stars. Our solar system plows through the interstellar medium at 43,000 miles per hour. This motion compresses the material ahead of us, like air warming inside a bicycle pump. Squeeze gas and it heats up. The same principle works on cosmic scales. Additionally, supernova explosions that carved out the local bubble millions of years ago injected tremendous energy into the surrounding space. That energy still lingers, keeping the medium warmer than it would naturally be. The temperature mystery connected to another puzzle that had been growing since the termination shock. If the boundary was this hot, if compression and reconnection were generating this much energy, then the heliopause should be a violent place. Not a quiet membrane separating two calm environments, but a turbulent frontier crackling with energy. And that is exactly what Voyager found when it finally crossed through. The heat was a warning sign, a signal that the edge of our solar system is not an ending, but a collision. two environments smashing into each other at cosmic speeds, generating temperatures that dwarf the surface of some stars. The equations that promised cold were based on assumptions of simplicity. Reality, as Voyager kept proving, is never simple, and the heat had one more secret to share. It was not spread evenly across the boundary. Some regions burned hotter than others. The heliopause had hot spots and cool spots, regions where reconnection was fiercer and regions where compression was gentler. The boundary was not uniform. It was patchy, inconsistent, and alive with variation. This would become even clearer when Voyager 2 crossed the boundary years later and measured temperatures nearly 2.5 times cooler than its twin. The edge of everything we call home was burning, and Voyager flew straight through the flames. Every scientist who studied the heliosphere before Voyager arrived at the edge, drew the same shape, a sphere, maybe slightly elongated like an egg, maybe stretched into a teardrop by our motion through the galaxy, but fundamentally round, symmetric, predictable. The sun sits at the center. The solar wind blows outward equally in all directions. The interstellar medium pushes inward equally from all sides. The result should be a balanced bubble. A neat, tidy boundary separating our star's influence from everything else. Voyager destroyed that picture completely. The first clue came from comparing the two spacecraft. If the heliosphere was symmetric, both Voyagers should have encountered the termination shock at roughly the same distance. They did not. Voyager 1 crossed it at 94 astronomical units. Voyager 2 crossed at 84. That 10-unit difference represents nearly 1 billion miles, a gap so enormous that no symmetric model could explain it. The bubble was not round, it was lopsided. The reason involves something easy to forget. Our solar system is not sitting still. It moves through the galaxy at 43,000 miles per hour, orbiting the galactic center in a vast circle that takes 230 million years to complete. As we move, we plow into the interstellar medium. The material ahead of us gets compressed. The material behind us gets stretched. This creates asymmetry. The side of the heliosphere facing our direction of travel gets squashed inward. The opposite side, the tail, gets pulled outward. Voyager 1 traveled through the compressed nose region. Voyager 2 traveled through the flank, closer to the stretched tail. Same bubble, different thicknesses, different distances to the boundary. The heliosphere is not a sphere at all. It is squashed in front and elongated behind. Some new models show it shaped like a croissant, flattened at the leading edge with a long, possibly fragmented tail trailing behind like a comet. That word fragmented is important. Some computer simulations suggest the tail of the heliosphere does not hold together as a single structure. Instead, it may break apart into multiple lobes, twisted and separated by magnetic forces. Imagine a flag in a strong wind. The front stays rigid where the pole holds it, but the trailing edge tears into ribbons that whip independently. The heliosphere's tail might behave the same way, compressed and stable at the nose, torn and chaotic at the rear. Radio astronomers tried to observe the heliosphere from outside. They used distant pulsars whose regular radio pulses pass through our solar system's edge. By measuring how those pulses change, scientists hoped to map the boundary. The results were confusing. The boundary appeared to be in different locations depending on which direction they looked. It moved. It shifted. It behaved nothing like a stable structure. Voyager's data explained why. The heliosphere breathes. It responds to the 11-year solar cycle. During solar maximum, when our star is most active, the solar wind blows harder. The boundary pushes outward by billions of miles. During solar minimum, the wind weakens and interstellar pressure shoves the boundary inward. The heliosphere expands and contracts like a lung, but the breathing is not smooth or uniform. It happens at different rates in different directions, depending on local conditions in the interstellar medium. Every 11 years, something else happens. The sun's magnetic field flips. North becomes south. South becomes north. This reversal sends shock waves rippling through the entire heliosphere, disrupting the boundary for months. Voyager detected these disruptions as sudden changes in particle density and magnetic field direction. The edge of our solar system shakes every time the sun's magnetic poles swap places. This breathing pattern has consequences that reach all the way back to Earth. The heliosphere's shape determines how cosmic rays enter our neighborhood. Cosmic rays do not penetrate the bubble evenly. They enter more easily through the nose, where the compressed magnetic field can develop gaps and weak points. They enter less easily through the tail, where the stretched magnetic field lines create a tangled barrier. This means Earth's cosmic ray exposure varies depending on which part of the heliosphere faces the incoming radiation at any given time. During solar minimum, when the heliosphere shrinks, cosmic rays flood inward from all directions. More radiation reaches the inner solar system. More particles strike Earth's atmosphere. As scientists have measured this effect using ground-based detectors, cosmic ray counts on Earth rise and fall in rhythm with the solar cycle. When the sun is quiet, radiation goes up. When the sun is active, radiation goes down. Some researchers propose that these variations affect Earth's climate. The theory suggests that cosmic rays seed cloud formation by ionizing molecules in the atmosphere. More cosmic rays mean more ions. More ions mean more cloud condensation nuclei. More clouds mean more sunlight reflected back into space. More reflection means cooler temperatures. The idea remains controversial. Many climate scientists argue that the effect is too small to matter compared to other factors like greenhouse gases and ocean currents. But the hypothesis exists, and Voyager's data provides the baseline measurements needed to test it properly. The shape of the heliosphere also matters for understanding other star systems. Every star with a stellar wind creates its own bubble, but their shapes depend on countless factors: the star's strength, the density of surrounding space, the direction of travel through the galaxy, the local magnetic field. No two heliospheres are alike. Some might be nearly spherical if the star moves slowly through thin space. Others might be violently compressed if the star races through dense material. When telescopes observe bow shocks around distant stars, glowing arcs of heated gas visible in infrared, they see evidence of compressed heliospheres, stars plowing through dense regions at high speed. When no shock is visible, it might mean the star occupies a thin region, like our own local fluff. The environment shapes the bubble as much as the star itself. Our bubble is stranger than anyone imagined, compressed at the front, stretched at the back, possibly torn into ribbons along the tail, breathing with every solar cycle, shaking with every magnetic reversal, leaking cosmic rays through gaps that shift and wander. And at every point along its surface, conditions differ. Temperature varies, pressure varies, magnetic field strength varies. The boundary is not a wall. It is a weather system on a cosmic scale, driven by forces from both inside and outside. Voyager measured 2 tiny points along this vast, shifting surface, 2 points separated by billions of miles, each telling a different story. And those 2 stories were enough to overturn decades of assumptions about the shape of our cosmic home. The heliosphere is not the neat bubble drawn in textbooks. It is a wild, asymmetric, breathing structure that protects us from the full fury of galactic radiation while constantly reshaping itself in response to forces we are only beginning to understand. And Voyager was about to punch through its outermost wall. The spacecraft had spent years in the magnetic highway, that strange corridor between worlds. Now the data pointed towards something final. Cosmic ray counts were climbing sharply. Solar particle counts were falling fast. The instruments sensed a threshold approaching, not gradually, but with increasing urgency. The numbers converged toward a moment of transformation that would mark the most distant milestone in the history of human exploration. August 25th, 2012, a date that belongs in the permanent record of human achievement. On this day, 13 billion miles from the nearest human heartbeat, an instrument panel on a spacecraft built before the invention of the personal computer registered a sudden shift. The number of solar particles striking Voyager 1 dropped by half in a single day. Not a gradual decline, not a slow fade, a cliff. One moment, detectors counted thousands of solar particles per second. The next, they counted hundreds. Something fundamental had changed in the space surrounding the spacecraft. At the same moment, galactic cosmic rays surged. These particles, born from exploding stars and violent collisions across the Milky Way, had been rising for months. But on this day, they jumped 30% in hours. The balance between inside and outside had tipped. Solar influence was collapsing. Galactic influence was flooding in. Voyager stood at the threshold, but not everyone agreed that the crossing had happened. The science team split into camps. The particle data screamed that Voyager had left the heliosphere. Solar particles vanishing, cosmic rays surging. The signatures were dramatic and clear, yet the magnetic field measurements told a contradictory story. The magnetometer detected no change in field direction. The solar magnetic field, which had guided Voyager for 35 years, still pointed the same way. If the spacecraft had truly entered interstellar space, the magnetic field should have rotated. It should have aligned with the interstellar field, which originates from galactic structure and points in a completely different direction. For months, the debate consumed the heliophysics community. Papers were published arguing both sides. Press conferences delivered cautious, contradictory messages. NASA hesitated to make an official announcement. Had Voyager crossed, or had it not? The data seemed to argue with itself. Particles said yes. Magnetics said no. Both instruments worked perfectly. Both measurements were accurate. The universe was speaking with two voices at once. Then, in April 2013, nature provided the answer. A massive solar eruption blasted billions of tons of plasma outward from the sun's surface. This coronal mass ejection raced through space at millions of miles per hour. When it reached the heliosphere's edge, it struck the boundary like a hammer hitting a gong. The shockwave crossed the heliopause and disturbed the plasma on the other side. Voyager detected the disturbance, but not as particles or magnetic fields. It detected vibrations. The plasma surrounding the spacecraft began to oscillate at a specific frequency. Scientists could measure that frequency precisely, and frequency reveals density. The denser the plasma, the higher the frequency of oscillation, like tapping a glass of water versus tapping an empty glass. The full glass rings at a higher pitch. The frequency Voyager measured was 40 times higher than anything recorded inside the heliosphere. 40 times. Not a subtle difference. Not a marginal increase. A transformation. The spacecraft was surrounded by plasma 40 times denser than what exists inside the solar bubble. This was interstellar plasma, material from between the stars, substance that had never known the touch of our sun. That measurement settled the debate. Voyager 1 had crossed the heliopause in August 2012. The plasma density proved it beyond any doubt. Humanity had sent a machine past the outermost boundary of our star's domain. For the first time in history, a human creation existed in interstellar space. But the magnetic field puzzle remained. Why had the field not rotated when Voyager crossed? The answer turned out to be cosmic coincidence. Or in the particular region where Voyager 1 exited the heliosphere, the interstellar magnetic field happened to point in the same direction as the solar magnetic field. By pure chance, the two fields were aligned. So even though Voyager passed from one magnetic environment to another, the magnetometer could not detect the change. The field direction stayed the same because both sides pointed the same way in that location. This coincidence nearly derailed one of the greatest discoveries in space exploration. If scientists had relied only on the magnetometer, they might have concluded Voyager was still inside the heliosphere. Only the plasma oscillation measurement revealed the truth. Sometimes the most important answer comes from the instrument you least expect. 6 years later, Voyager 2 provided confirmation from a completely different angle. In November 2018, Voyager 2 crossed the heliopause at 119 astronomical units, 3 astronomical units closer to the Sun than its twin. When Voyager 2 crossed, its magnetometer did detect a rotation. The magnetic field shifted direction over several days, gradually aligning with the interstellar field. The two fields were not aligned in Voyager 2's region. The rotation was clear, unmistakable. The crossing was confirmed by every instrument simultaneously. The contrast between the two crossings revealed something essential. The heliopause is not uniform. It varies from place to place. In one location, the magnetic fields happen to align. In another, they clash. The boundary has different properties at different points along its surface. No two crossings will ever be identical. The crossing itself was not instantaneous. Voyager did not pop through a membrane like a needle through fabric. The transition happened over a zone roughly 3 astronomical units thick, nearly 300 million miles of turbulent space where solar and interstellar influences mixed together. Particles from both environments swirled in the same volume. Magnetic field lines tangled and reconnected. Energy released in bursts. Voyager spent weeks in this transition zone, instruments recording every fluctuation, every spike, every dip. What surprised the science team most was how active the boundary was. They had expected a calm interface, a quiet membrane separating two still environments. Instead, they found chaos. Waves propagated through the plasma constantly. Particles accelerated to high energies. The boundary rippled and shifted by billions of miles, depending on solar activity. It was not a wall separating two rooms. It was a battlefield where two cosmic armies met, and neither retreated. The plasma density measurement that confirmed the crossing also revealed the character of interstellar space. Voyager measured approximately 0.13 particles per cubic centimeter outside the heliopause. That sounds impossibly thin. And it is thin. A cubic centimeter of air at sea level contains about 25 billion molecules. Interstellar space contains a fraction of one particle in the same volume. Yet that fraction is enough. Enough to stop the solar wind. Enough to compress the heliosphere. Enough to create pressure that shapes the boundary of our entire star system. Voyager 1 now travels through this medium. Every day, it moves farther from home. Every day, the distance grows by roughly 1 million miles, and every day, data streams back at 160 bits per second. Measurements of a place no human will visit for centuries. Perhaps millennia. Perhaps ever. But Voyager is there, measuring, transmitting, proving that the edge of our solar system is not an ending, but a beginning. The crossing was violent, ambiguous, and beautiful. And what waited beyond was stranger still. Cosmic rays are the universe's invisible artillery. They are not rays at all despite the name. They are particles, atomic nuclei stripped of their electrons, accelerated to nearly the speed of light by the most violent events in the cosmos. Exploding stars, colliding galaxies, supermassive black holes devouring matter at the centers of distant star systems. These events launch particles across the universe with energies so extreme that a single cosmic ray smaller than an atom can carry the kinetic energy of a baseball thrown at 60 miles per hour. When one strikes Earth's atmosphere, it shatters into a cascade of millions of secondary particles, raining down to the ground like invisible shrapnel. We survive this bombardment because of our shield. The heliosphere deflects most cosmic rays before they reach the inner solar system. The solar wind and its tangled magnetic field bend the paths of incoming particles, turning them aside like a river diverting around a stone. Only the most energetic cosmic rays punch through. Earth's own magnetic field provides a second layer of defense, and our atmosphere absorbs most of what remains. Layer upon layer of protection. Without these shields, surface radiation would be far higher. Life as we know it might never have evolved. Voyager carried cosmic ray detectors specifically designed to count particles and measure their energy. As the spacecraft traveled outward, scientists tracked the count carefully. Near Earth, the detectors registered around 100 million cosmic rays per square meter per second. That sounds like a lot, but most carry low energy. They bounce off human cells without causing damage. Only the rare high-energy particles pose real danger. As Voyager moved farther from the Sun, the count rose, but not smoothly. Scientists had predicted a gradual ramp, a steady increase as the heliosphere's shielding thinned with distance. Instead, the data showed a staircase pattern, sharp jumps separated by flat plateaus. Each step corresponded to Voyager entering a new region with different magnetic properties and different shielding effectiveness. The termination shock was one step. Cosmic rays jumped as Voyager crossed it. The magnetic highway was another step. Some particles flowed freely along the corridor, boosting counts further. The heliopause was the final and most dramatic step. After crossing into interstellar space, cosmic ray levels jumped to approximately 900 million particles per square meter per second, nearly 9 times higher than near Earth. This is the baseline radiation of interstellar space. Everything beyond the heliosphere experiences this bombardment constantly. Every rock, every dust grain, every rogue planet drifting between the stars, bathed in radiation from every direction with no shield and no shelter. The energy spectrum changed dramatically too. Inside the heliosphere, Voyager detected mostly lower energy cosmic rays. The heliosphere filters out the weakest particles while allowing the strongest through. Outside, Voyager detected the full range, including ultra-high energy cosmic rays with energies exceeding billions of electron volts. These particles carry so much energy that a single one striking a human cell could shatter DNA strands and cause catastrophic biological damage. Scientists traced the origins of these cosmic rays. Most come from supernova remnants within our own galaxy. When a massive star collapses and explodes, the blast creates a shockwave that expands outward for thousands of years. This shockwave accelerates particles to extraordinary speeds. The Milky Way contains roughly 300 billion stars. Hundreds explode every century. Each explosion seeds the galaxy with fresh cosmic rays that travel for millions of years before losing energy. Some cosmic rays come from even farther away. Extragalactic cosmic rays originate in other galaxies, possibly from jets of material blasting out of supermassive black holes, possibly from collisions between entire galaxy clusters. These are the rarest and most energetic particles in the universe. Voyager detected a handful of them. Confirmation that particles accelerated in distant galaxies can reach our local neighborhood of space. But the cosmic ray data revealed something more important than origins. It revealed the heliosphere's weaknesses. Cosmic rays do not penetrate the bubble evenly. They find gaps. They exploit weak points in the magnetic field, the compressed nose of the heliosphere, where our motion through the galaxy squeezes the field lines together, develops cracks that cosmic rays slip through. The stretched tail offers different vulnerabilities where tangled field lines create corridors of easier access. This uneven penetration means Earth does not receive the same cosmic ray dose at all times. The dose varies with the solar cycle. During solar minimum, when the heliosphere shrinks and the magnetic field weakens, more cosmic rays reach the inner solar system. During solar maximum, when the bubble expands and the field strengthens, fewer get through. Ground-based neutron monitors have measured this rhythm for decades. Cosmic ray counts on Earth's surface rise and fall in an 11-year pattern that mirrors the Sun's activity cycle exactly. Some scientists have proposed a controversial connection. They suggest cosmic ray variations might influence Earth's climate. The mechanism involves cloud formation. When cosmic rays enter the atmosphere, they ionize air molecules. These ions can act as seeds around which water vapor condenses, forming cloud droplets. More cosmic rays could mean more clouds. More clouds reflect more sunlight back into space. More reflection means cooler surface temperatures. The theory suggests that during periods of weak solar activity, when more cosmic rays reach Earth, cloud cover increases and the planet cools slightly. The idea remains hotly debated. Many atmospheric scientists argue that the effect is too small to compete with other climate drivers like carbon dioxide concentrations and ocean circulation patterns. Laboratory experiments have shown that ionization can indeed promote droplet formation under controlled conditions. But whether this translates to measurable climate effects on a planetary scale is uncertain. Voyager's cosmic ray measurements provide the critical baseline data needed to test these ideas. By knowing exactly how many cosmic rays exist in interstellar space and how effectively the heliosphere blocks them, scientists can model different scenarios with greater precision. Voyager also detected something puzzling in interstellar space itself. The cosmic ray count fluctuated over days and weeks, even beyond the heliopause. This means the interstellar medium is not uniform. Some regions are denser and partially block cosmic rays. Others are emptier and let more through. The spacecraft flies through this invisible patchwork, encountering different environments as it goes. Each fluctuation reveals structure in the space between stars. Clouds and voids too subtle for telescopes to see, but detectable by a machine flying through them. The cosmic ray detectors continue counting. Each particle that strikes the spacecraft tells a story. Where it came from, how fast it traveled, what accelerated it. Some particles have been traveling for millions of years, crossing the entire galaxy before hitting Voyager's silicon sensors. Others are younger, launched by relatively recent supernovae only thousands of light years away. Together, they paint a picture of a galaxy alive with violence and energy. A galaxy where the space between stars is not empty but filled with the debris of stellar death. And that debris rains down on our small world constantly, filtered by a bubble that breathes and shifts, modulated by a star that waxes and wanes. Voyager measures the rain from outside the umbrella, and the rain is heavier than anyone expected. In space, no one can hear you scream. That famous line captures what most people believe about the void between worlds. Space is silent, space is empty. Sound needs air to travel, and there is no air beyond our atmosphere. This is true in the way most people understand sound. Pressure waves moving through gas, vibrating eardrums, creating the experience of hearing. By that definition, space is indeed silent, but Voyager proved that silence is an illusion. In 2012, our star erupted. A massive coronal mass ejection blasted billions of tons of superheated plasma outward from the solar surface. This wall of charged material raced through the heliosphere at over 1 million miles per hour. It crossed the orbits of the inner planets in hours. It passed Jupiter in days. It reached the outer heliosphere in weeks. And when it struck the heliopause, the outermost boundary of our solar system, something remarkable happened. The shock wave did not stop at the boundary. It punched through, and on the other side, it disturbed the interstellar plasma. The charged particles in that region began to vibrate. They compressed and expanded in rhythmic waves, oscillating at a specific frequency determined by the density and temperature of the medium surrounding them. These oscillations propagated outward through the interstellar plasma, like ripples spreading across the surface of a pond after a stone drops in. Voyager 1, already in interstellar space, detected these vibrations. The plasma wave instrument measured oscillations at a frequency of 2.6 kHz, far too high for human ears to hear, even if there were air to carry the sound. But scientists can shift frequencies into audible range using computers. When they did, they heard something haunting, a rising tone, a whistle climbing upward in pitch, the sound of the heliosphere ringing like a bell struck by the fist of our own star. This was not the first time Voyager detected plasma oscillations. In 2013, another solar eruption sent a second shockwave through the heliopause. Again, Voyager measured the resulting vibrations. Again, the frequency revealed plasma density with extraordinary precision. By analyzing the pitch of the oscillation, scientists calculated exactly how dense the interstellar plasma was in that region. The answer matched the direct measurements from the plasma sensor perfectly. Two completely different instruments confirming the same number. The technique worked beautifully, but the truly remarkable discovery came later. When scientists went back through Voyager's data more carefully, searching for weak signals buried beneath the noise, they found something unexpected. A faint oscillation that had been present all along, not triggered by solar eruptions, not caused by any specific event, just a constant, quiet vibration in the interstellar plasma, a persistent hum that never stopped. The frequency was much lower, around 300 Hz, a background drone woven into the fabric of interstellar space itself. The hum of the universe between the stars, constant and unending, like the low note of a pipe organ played in a cathedral so vast that the walls disappear into darkness. What causes this eternal hum? The interstellar medium is not still. It flows. Turbulence stirs it. Magnetic fields shift through it. Shock waves from distant supernovae propagate across light years, weakening as they travel but never fully disappearing. All of these processes create low-frequency oscillations that ripple through the plasma. They overlap and interfere, creating a complex background vibration that fills interstellar space. Voyager happened to drift into a region where these background waves converged into a detectable signal. The sound is real, though calling it sound requires stretching the definition. Sound on Earth means pressure waves traveling through air. Molecules push against neighboring molecules, transferring energy from point to point until the wave reaches your eardrum. In interstellar space, charged particles play the role of air molecules. They push against each other through electromagnetic forces rather than physical collisions. The physics is analogous. The mechanism is different, but the result is similar. Waves of compression and expansion moving through a medium, carrying energy across vast distances. If you could somehow float in interstellar space and survive, you would not hear this hum. The plasma is far too thin. There are not enough particles per cubic centimeter to transfer pressure to an eardrum, but instruments can detect it, and those instruments reveal a universe that hums and vibrates and resonates with energy at every scale. NASA released recordings of these sounds to the public. Engineers converted the plasma oscillation data into audio files. People could listen to the heliosphere ringing after a solar eruption. They could hear the rising whistle of shock waves passing through interstellar plasma. They could hear the low background hum of the space between stars. The recordings went viral. Millions of people around the world listened to the sound of interstellar space for the first time in human history. Some found it eerie, a low, droning vibration that seems to come from everywhere and nowhere, like standing in an empty building and hearing the walls breathe. Others found it beautiful, proof that the universe is not the cold, dead silence we imagined. Space is active, alive with energy and motion and vibration. The void sings, and Voyager was the first machine to hear its song. The plasma oscillations also serve a practical scientific purpose beyond their haunting beauty. By measuring the frequency of these vibrations, scientists can map plasma density across vast regions of space without needing to fly through them directly. Radio telescopes on Earth can detect similar oscillations from distant sources. Stars that erupt and disturb surrounding plasma create oscillations that travel outward for light years. By measuring those frequencies, astronomers calculate plasma density along the line of sight. Combined with Voyager's direct measurements from inside the interstellar medium, this technique creates a three-dimensional picture of the local neighborhood between stars. Dense regions vibrate at higher frequencies. Thin regions vibrate at lower frequencies. The oscillations become a diagnostic tool, revealing properties of the medium that would otherwise require sending a spacecraft to every location. Future spacecraft could even use plasma oscillations for navigation. As a probe flies through interstellar space, the frequency of background oscillations would change as density changes. By monitoring these shifts, a spacecraft could determine when it enters denser or thinner regions without needing dedicated plasma sensors. The hum of space itself becomes a map. Voyager keeps listening. The plasma wave instrument still functions, still recording every oscillation, every fluctuation in the interstellar medium. Somewhere in that continuous stream of data, hidden beneath the noise, might be signals from events we have not yet identified. Shock waves from supernovae that exploded thousands of years ago finally reaching our neighborhood. Collisions between interstellar clouds compressing plasma in distant regions. Magnetic reconnection events on scales spanning light years. Each event sends vibrations through the medium. Each vibration carries information. Space is not silent. It never was. We just needed to send a machine far enough to hear what had been playing all along. A symphony written in plasma, performed across light years, heard by a single aging spacecraft drifting through the dark with its instruments turned toward the void and its antenna turned toward home. And beneath the hum, beneath the whistles and the rising tones, another question waited. If the heliosphere rings when struck, what else might strike it? What other forces shape our bubble from the outside? Voyager had already proven that temperatures and shapes defied prediction. Now it was about to reveal that one of the most fundamental predictions about our solar system's interaction with the galaxy was simply wrong. When a boat moves through water, it creates a wave at the front, a bow wave. The faster the boat moves, the sharper the wave becomes. At high enough speeds, the wave steepens into a shock front, a sudden wall of compressed water that pushes outward from the bow. This is basic physics. Motion through a medium creates compression ahead and a wake behind. Every student learns this. Every model predicts it. Our solar system moves through the interstellar medium at 43,000 miles per hour. We orbit the galactic center, plowing through the thin gas and plasma that fills the space between stars. Every model of the heliosphere predicted that this motion should create a bow shock ahead of us, a distinct wall of compressed interstellar material piling up in front of the heliosphere like snow before a plow. Observations of other stars confirmed the idea. Infrared telescopes captured beautiful images of distant stars surrounded by glowing arcs of heated gas. Clear, unmistakable bow shocks created by stellar motion through denser regions of space. Scientists calculated exactly where our bow shock should be, approximately 230 astronomical units from the Sun, roughly twice the distance where Voyager crossed the heliopause. The math was clean. The physics was well understood. The bow shock should exist. It had to exist. Our motion demanded it. Voyager flew through the region where the bow shock should have been, and it found nothing. No sudden jump in pressure, no sharp temperature spike, no abrupt change in density that would indicate a shock front. The instruments measured only gentle, gradual variations spread across billions of miles. The space ahead of our solar system was quiet, undisturbed. The dramatic wall of compressed material that every model predicted simply was not there. At first, scientists thought Voyager had missed it. Space is enormous. The bow shock might curve around the heliosphere in a shape that Voyager's trajectory did not intersect. Perhaps the spacecraft passed through a gap or a weak point in the shock. But as months passed and data accumulated, a different conclusion emerged. The bow shock does not exist. Not in the way models predicted. Not as a sharp, as well-defined boundary. Perhaps not at all. The explanation lies in the peculiar region of the galaxy we currently occupy. Our solar system does not travel through average interstellar space. It moves through a region called the local fluff. This is a cloud of gas with remarkably low density, about 0.3 atoms per cubic centimeter. That is 100 times less dense than the thickest interstellar clouds elsewhere in the galaxy. For a bow shock to form, the medium ahead must be dense enough to pile up and compress sharply. If the medium is too thin, the compression happens gradually, spread across such a vast volume that no distinct shock front forms. Think of the difference between running through water and running through air. Water resists strongly. You feel immediate compression against your body. Air barely resists at all. You push through it easily with no sharp wave forming ahead of you. The local fluff is like air, too thin to create a sharp shock. Instead of a bow shock, Voyager detected what scientists now call a bow wave, a gentle, broad increase in density and pressure stretched across billions of miles. No sharp edge, no dramatic boundary, just a slow compression so gradual that instruments need years of data to detect it at all. This discovery was one of the most important findings of the entire mission, not because Voyager found something spectacular, but because it confirmed the absence of something everyone expected. And in science, the absence of something predicted can be as revolutionary as the presence of something unexpected. The missing bow shock forced a complete rethinking of how our solar system interacts with its environment. The interaction depends heavily on local conditions. When we pass through denser regions of the galaxy, a bow shock will form, sharp and bright and visible to distant telescopes. When we pass through thinner regions like the local fluff, it will not. We happen to live in a thin region right now, but this will change. Our solar system moves, the galaxy rotates. Over millions of years, we encounter different environments. Around 10,000 years ago, we exited a denser cloud called the local interstellar cloud and entered the current thin region. When that transition happened, the heliosphere likely expanded. Any bow shock that existed before probably faded as the surrounding density dropped. We have been traveling through relatively empty space ever since, but in the future, we will exit the local fluff and enter another denser region. When that happens, the heliosphere will compress. A bow shock will reappear. Cosmic ray levels reaching Earth will increase as the shrinking bubble provides less shielding. Scientists estimate this transition might happen in the next 10 to 20,000 years. A blink in cosmic terms, though far beyond any human lifetime. This realization transformed how astronomers interpret observations of other star systems. When telescopes detect bright bow shocks around distant stars, it means those stars are racing through dense regions of the galaxy. The shock is a sign of environment, not just stellar power. When no shock is visible, it does not mean the physics is wrong. It means the star occupies a thin region where compression is too gradual to produce a sharp front. The environment matters as much as the star itself. The missing bow shock also connected to the heliosphere's breathing pattern. During solar maximum, when the solar wind strengthens, the heliosphere pushes outward. If a bow shock existed, it would push outward too, compressing more interstellar material. During solar minimum, both would contract, but without a sharp shock, the interaction is softer. The heliosphere gently displaces the thin local fluff rather than crashing into it. This gentler interaction might explain why the heliopause itself is so dynamic. Without a rigid bow shock to stabilize the front end, the entire heliosphere is free to ripple and deform in response to every gust of interstellar pressure. Some theorists have proposed a speculative idea. Perhaps the absence of a bow shock makes our heliosphere more vulnerable to disruption than heliospheres around other stars. A sharp bow shock acts like a bumper on a car. It absorbs the impact of incoming material before it reaches the main structure. Without that bumper, interstellar disturbances can reach the heliopause more directly. Shock waves from distant supernovae, density variations in passing clouds, magnetic field fluctuations from galactic structure. All of these might affect our heliosphere more strongly because we lack the protective cushion that a bow shock provides. Whether this vulnerability has consequences for Earth is an open question. The heliosphere still provides substantial shielding against cosmic rays. The magnetic field still deflects incoming particles. But the shield might be more fragile than we assumed, more responsive to external changes, more susceptible to sudden compressions that let bursts of cosmic radiation through. Voyager could not answer all these questions with a single trajectory, but it established the fundamental fact. Our solar system currently moves through the galaxy without a bow shock. The space ahead of us is quiet. No wall of compressed material announces our passage through the stars. We drift through the local fluff like a whisper through an empty room. And that quiet space held more surprises, because when Voyager 2 finally crossed the heliopause 6 years after its twin, it told a very different story about the boundary itself. 2 spacecraft, 2 paths, 2 crossings, and almost nothing in common except the destination. Voyager 1 and Voyager 2 both left the heliosphere, both entered interstellar space, both sent data back confirming the crossing. But the stories they told were so different that scientists could barely believe the same boundary produced both experiences. Voyager 1 crossed the heliopause in August 2012 at 122 astronomical units from the Sun. Voyager 2 crossed in November 2018 at 119 astronomical units, 3 astronomical units closer. That difference represents roughly 280 million miles, a gap that reveals how much the boundary shifts depending on where and when you cross it. The 6-year gap between crossings mattered enormously. When Voyager 1 crossed, the solar cycle was climbing toward maximum activity. The solar wind blew relatively hard, pushing the heliopause outward. When Voyager 2 crossed, the cycle had declined toward minimum. The wind weakened. Interstellar pressure pushed the boundary inward. The heliosphere had exhaled between crossings. It shrank by billions of miles. Voyager 2 met the boundary closer to home because the boundary itself had moved inward during the quiet years. But timing was not the only factor. The 2 spacecraft exited through different parts of the boundary. Voyager 1 flew upward out of the plane where planets orbit, exiting through the heliosphere's northern hemisphere. Voyager 2 flew downward, exiting through the southern hemisphere. These regions experience different pressures from the interstellar medium, different magnetic field configurations, different levels of compression and turbulence, same bubble, different neighborhoods along its surface. The cosmic ray data showed the first major difference. Voyager 1 detected a gradual increase in cosmic rays over many months before the final jump at the heliopause. The transition was drawn out, like climbing a long staircase one step at a time. Voyager 2 detected a much sharper transition. Cosmic ray levels jumped more abruptly. The staircase had fewer steps, and each step was taller. The boundary in Voyager 2's region was more defined, more compressed. The transition from inside to outside happened faster and more dramatically. The magnetic field measurements told the most striking story. Voyager 1 detected no change in magnetic field direction at the crossing. The solar field and the interstellar field happened to align in that region by cosmic coincidence. The magnetometer saw the same orientation on both sides. Scientists spent months arguing about whether the crossing had actually occurred because the magnetic signature gave no confirmation. Voyager 2 experienced the opposite. When it crossed, the magnetometer detected a clear rotation over several days. The magnetic field shifted direction by about 45 degrees, gradually aligning with the interstellar field. The transition was unmistakable. Every instrument on Voyager 2 agreed simultaneously. Particles changed, plasma density jumped, magnetic field rotated. The crossing was confirmed from every angle at once. Temperature measurements added another layer of contrast. Voyager 1 encountered extremely hot plasma near the boundary, temperatures exceeding 250,000 degrees. Evidence of intense magnetic reconnection and compression heating the boundary plasma to extreme levels. Voyager 2 detected cooler plasma in its crossing region, around 100,000 degrees, still hot by any earthly standard, but nearly 2.5 times cooler than what Voyager 1 measured. This temperature difference revealed that the heliopause has hot spots and cool spots scattered across its surface, regions where magnetic reconnection burns more fiercely, regions where compression is gentler. The boundary is not a uniform membrane with consistent properties. It is patchy, variable, different at every point along its vast surface. Plasma density showed similar variation. Voyager 1 measured interstellar plasma density at approximately 0.13 particles per cubic centimeter. Voyager 2 measured 0.09. Lower density means lower pressure in that region. This partly explains why Voyager 2 crossed closer to the Sun. Less external pressure meant the boundary could not push as far outward in that direction. The heliosphere bulged outward where pressure was lower and compressed inward where pressure was higher. The fine structure near the boundary differed dramatically as well. Voyager 1 spent roughly a month in the transition zone, that turbulent layer where solar and interstellar influences mixed together. For weeks, the instruments showed ambiguous readings. Sometimes solar particles dominated. Sometimes interstellar particles dominated. The boundary seemed to wash back and forth over the spacecraft like waves on a beach. One day, Voyager was inside. The next day, outside. Then, inside again. Voyager 2 spent only a few days in transition. The boundary was sharper in that location, more compressed by external forces. The spacecraft punched through quickly without the prolonged ambiguity its twin experienced. One theory suggests that the interstellar magnetic field was stronger in Voyager 2's region, squeezing the boundary into a thinner, more defined layer. Another theory proposes that solar activity had created a temporary bulge near Voyager 1, stretching the transition zone into a wider, more gradual crossing. Turbulence levels also differed. Voyager 1 measured wild fluctuations in magnetic field strength near the heliopause. Values changed by factors of 2 or 3 over just hours. The boundary in that region was chaotic. Magnetic field lines twisted and snapped constantly. Energy released in unpredictable bursts. Voyager 2 measured more stable fields. Smaller fluctuations, less chaos. The boundary was calmer in that neighborhood, less violent, more orderly. Comparing the two crossings allowed scientists to separate universal features from local variations. Some things appeared at both crossings: the increase in cosmic rays, the jump in plasma density, the transition from solar to interstellar magnetic influence. These are fundamental properties of the heliopause that exist everywhere along its surface. They define what the boundary is regardless of location. Other features were purely local: the exact distance of the crossing, the temperature of the boundary plasma, the sharpness of the transition, the presence or absence of magnetic field rotation, the level of turbulence. These varied between the two crossings and would likely vary at any other crossing point as well. The boundary is alive with local conditions that change from place to place and moment to moment. This distinction matters enormously for building accurate models. Scientists cannot assume the heliosphere has a fixed shape, or that the heliopause is uniform. Reality is messier, far messier. The boundary ripples and shifts. It responds dynamically to forces from both inside and outside. Solar eruptions push it outward. Interstellar pressure pushes it inward. Magnetic reconnection heats some regions while leaving others cool. The entire structure is in constant motion. Future missions would need far more than 2 data points to map this complexity properly. Dozens of spacecraft launched in different directions might be required to capture the full 3-dimensional structure and its evolution over time. Voyager gave us 2 points on a vast surface, 2 pins stuck into a globe the size of a solar system. Enough to prove the boundary exists and that it varies. Not nearly enough to understand its full architecture. But those 2 points changed everything. They revealed a heliopause that is not a wall but a living frontier. Dynamic and variable, and never the same twice. 2 spacecraft crossed the same boundary and told 2 completely different stories, and both stories were true. Every instrument aboard Voyager was built by human hands in the 1970s. Engineers used vacuum tubes for some circuits. Transistors were soldered individually by technicians peering through magnifying glasses. Computer memory was stored on magnetic tape. The entire onboard computer carries 68 kilobytes of memory. Your smartphone carries billions. A modern digital watch has more processing power than the machine currently exploring interstellar space. Yet this ancient technology still functions, 45 years in the most hostile environment imaginable. Temperature swings from boiling radiation near Jupiter to minus 270 degrees in the void between stars. Constant bombardment by cosmic rays that strike the spacecraft thousands of times per second. A micrometeorite impacts that pit the surface over decades. No maintenance, no repairs, no human hand reaching out to tighten a bolt or replace a worn component. Voyager endures alone. The secret is simplicity. The engineers who built Voyager followed a philosophy that modern spacecraft designers sometimes forget. Overdesign everything. Use robust materials. Avoid exotic technologies. If a simple solution works, use it. Do not be clever when reliable will do. This conservative approach looks primitive compared to today's spacecraft with their microprocessors, complex software, and integrated circuits. But simple systems have fewer ways to fail. A vacuum tube does not crash like software. A hand-soldered transistor does not suffer bit flips from cosmic ray strikes. Analog circuits degrade gradually, giving warning signs. Digital circuits can fail catastrophically without warning. The cosmic ray detector is essentially a solid-state telescope. Particles strike silicon sensors, creating tiny electrical pulses. The size of each pulse reveals the particle's energy. The rate of pulses reveals how many particles arrive per second. Simple concept. Reliable execution. The magnetometer uses coils of wire mounted on a long boom extending away from the spacecraft. When a magnetic field passes through a coil, it creates a voltage. Measure the voltage, and you know the field strength. 3 coils at different angles give you direction. The boom keeps the coils far from the spacecraft's own magnetic interference. Elegant and robust. The plasma sensor on Voyager 2 still works perfectly. 4 Faraday cups face different directions, catching charged particles and measuring their speed, density, and flow direction. Voyager 1's plasma sensor partially failed in 1980 when a circuit gave out. For decades, scientists thought they would lose critical data at the heliopause crossing. Then, solar eruptions created plasma oscillations that revealed density through frequency measurements instead. Luck and physics compensated for broken hardware. Power is the mission's ticking clock. Voyager runs on radioisotope thermoelectric generators, 3 units containing plutonium-238. As the plutonium decays, it produces heat. Thermoelectric couples convert that heat into electricity. No moving parts. No chemical reactions that can run out. Just the steady tick of nuclear physics. At launch, the generators produced 470 watts. Enough to power all instruments, the transmitter, heaters, and onboard computers simultaneously. Now they produce around 250 watts. The output drops by 4 watts every year as the plutonium decays. Nothing can stop it. Nothing can recharge it. The clock runs one direction only. Mission engineers manage this decline with painful precision. They calculate how much power each system needs. They prioritize ruthlessly. The transmitter is essential. Without it, Voyager becomes a silent ghost. The plasma sensor and magnetometer come next. They provide the most valuable scientific data. The cosmic ray detector stays on because it uses minimal power. Everything else is negotiable. In 2007, engineers turned off the tape recorder used to store data. In 2008, the planetary radio astronomy instrument went dark. In 2020, the ultraviolet spectrometer was shut down. Each shutdown diminishes what Voyager can observe, but extends the mission by precious years. The engineers trade capability for time. Less vision, but more life. By 2025, power will drop too low to run heaters for most systems. The spacecraft will begin freezing. Components will operate at temperatures far below their design specifications, minus 150 degrees or colder. Engineers have tested similar components on Earth and found they sometimes survive well beyond rated limits. A circuit designed for minus 50 might function at minus 100, maybe longer. Nobody knows until it fails. Voyager has already operated colder than any specification allowed and kept transmitting. The thrusters present another challenge. Voyager must keep its antenna pointed at Earth. If the antenna drifts even a few degrees, the signal becomes too weak to detect across 13 billion miles. Tiny thruster firings correct the orientation, but thrusters burn fuel. The fuel supply was designed for 30 years. It has lasted 45. Reserves are critically low. Every firing must be calculated months in advance to minimize waste. In 2017, one set of primary thrusters showed signs of clogging. Decades of residue buildup had reduced their efficiency. Engineers activated backup thrusters that had been dormant since 1980. 37 years of silence. Then, a command crossed 13 billion miles of space, and the old thrusters fired perfectly. This bought more time, but time is finite. The transmitter deserves special attention. It broadcasts at 23 watts, less power than a refrigerator light bulb. This faint signal crosses 13 billion miles, spreading thinner with every mile. By the time it reaches Earth, the power is roughly a billionth of a watt. Only the 70-meter dish antennas of the Deep Space Network can detect something that faint. These antennas are among the most sensitive receivers ever constructed. They can detect signals weaker than a snowflake landing on grass. The transmitter uses a traveling wave tube amplifier, a vacuum tube device. Radiation hard because it has no semiconductor junctions to damage. Cosmic rays pass through with minimal effect. This is why the transmitter still functions perfectly after 45 years. But its power supply contains semiconductors that could fail eventually. If the power supply dies, the transmitter dies with it. Voyager would go silent, even if the generators still produced electricity. The final commands are already written. They sit on computers at NASA's Jet Propulsion Laboratory in Pasadena, California. When power drops too low to operate any instruments, controllers will send one last sequence. It will shut down everything except the transmitter. No sensors, no heaters, no attitude control, just a carrier signal. A tone broadcasting into space that says nothing except, "I am here." Engineers estimate this bare configuration might last until around 2038 or 2040. Then, even the tone will fade. Power will drop below the minimum needed to amplify radio waves. The signal will weaken over weeks. Ground controllers will watch it diminish on their screens, and one day the line will go flat. Silence, permanent and total. Engineers who started their careers analyzing Jupiter data in the 1980s will watch the signal disappear. Some have spent their entire professional lives with this spacecraft, checking data every morning, sending commands, troubleshooting problems across billions of miles with a 42-hour response delay. When the signal stops, they will feel it personally. Like losing a companion they spoke with every day for decades. But the spacecraft will not stop. It will keep flying at 38,000 miles per hour. Nothing to slow it down, no air resistance, no friction, just momentum carrying it forward through interstellar space forever. Silent and dark and enduring. After the signal fades, after the last instrument goes dark, after the final command crosses 13 billion miles and receives no answer, Voyager will still carry something. Not data, not measurements, not the faint hum of electronics. It will carry a message, a golden record spinning silently in its protective aluminum cover. 12 inches of copper plated in gold. Grooves pressed into its surface carrying the sound of a world that the spacecraft left behind nearly half a century ago. The record was never really meant for aliens. The chances of anyone finding Voyager in the vastness of interstellar space are essentially zero. The spacecraft is smaller than a car. Space is incomprehensibly large. The nearest star system, Alpha Centauri, is 25 trillion miles away. Yet Voyager is not even heading in that direction. In 40,000 years, it will pass within 1.6 light-years of a dim red dwarf called Gliese 445. That is still 9.4 trillion miles, far too distant for any star's gravity to capture the spacecraft. Voyager will sail past in the dark, unseen, undetected. A grain of metal in an ocean of nothing. In 300,000 years, it will drift near another star, then another. Over millions of years, it will wander through the galaxy, pulled by gravity from distant objects but never captured. It will share the void with billions of other wanderers. Rogue planets ejected from their home systems, brown dwarfs too small to ignite fusion, asteroids scattered by gravitational chaos. Some estimates suggest there are more rogue planets than stars in the Milky Way. Frozen worlds drifting in permanent darkness. Voyager will pass among them, invisible to each other, ships in an infinite night. Dust grains will strike the spacecraft occasionally, maybe once a month. Each impact deposits a tiny amount of energy, slowly eroding the surface over millions of years. The golden record might accumulate microscopic pits. The protective cover might thin gradually. But the damage happens so slowly that significant erosion takes millions of years. Gold does not corrode in vacuum. There is no oxygen to oxidize it, no water to rust it, no atmosphere to weather it. Cosmic rays will gradually damage the molecular structure at the atomic level. But this process takes billions of years. The record should remain playable for at least 1 billion years, possibly much longer. Carl Sagan led the team that selected the record's contents. They faced an impossible task. How do you represent all of humanity in 90 minutes of audio and 116 images? What music speaks for an entire species? What sounds capture a world? They chose Beethoven and Bach, Chuck Berry and Peruvian panpipes, a Navajo night chant and Japanese shakuhachi, pygmy initiation songs and Indian raga. Each piece chosen not for popularity, but for what it reveals about the human capacity to create beauty from vibration and breath. The images include mathematical definitions so that any intelligence could decode them. Diagrams showing DNA structure, human anatomy, animals grazing on open plains, forests and oceans and deserts, cities at night glowing with electric light, a woman nursing an infant, a family sharing a meal. The diversity of life on a pale blue world, orbiting an ordinary yellow star in the outer arm of a spiral galaxy. Spoken greetings in 55 languages span thousands of years of human communication, from ancient Sumerian to modern Mandarin. Each speaker says something simple. Hello, peace, friendship, we wish you well. The messages are hopeful, naive perhaps, sincere certainly. A species reaching into the dark and saying, we are here and we mean no harm. The record also carries natural sounds. Thunder, wind, rain, a surf breaking on a shore, birds singing at dawn, whales calling across ocean depths, the heartbeat of a mother recorded while she thought about the child growing inside her. These sounds require no translation. They are the voice of a living world, the only living world we know. Critics pointed out the absurdity. Any species capable of intercepting Voyager would have technology far beyond ours. They would not need crude analog recordings to understand life on Earth. They would have better instruments, better methods, better ways to study distant worlds. The record would be a curiosity at best, a primitive artifact from a primitive civilization. But the record was never for them. It was for us. The act of creating it mattered more than the destination. It forced humanity to ask what is truly important, what defines us, what we would choose to represent ourselves if we had one chance to speak to the universe. The answer was music, language, science, nature, family, the sound of rain and the cry of a newborn child. These are what we chose. These are what we sent into the void. Jimmy Carter's message etched into the record reads in part, "We are attempting to survive our time so we may live into yours." Written during the Cold War when nuclear annihilation felt possible any given Tuesday. The words carry more weight with each passing decade. Climate change accelerates, biodiversity collapses, new threats emerge that the 1977 team could not have imagined. We are still attempting to survive our time. The jury remains out on whether we will succeed. But Voyager flies on regardless of what happens behind it. The record does not know if humanity survives. It does not care. It simply carries its cargo forward through the dark. A bottle thrown into the cosmic ocean by a species standing on the shore of a small world wondering if anyone else is out there. The spacecraft drifts through the local interstellar cloud, a region of slightly denser gas within the vast local bauble carved out by ancient supernovae millions of years ago. In 10 to 20,000 years, our solar system will exit this cloud entirely and enter the hotter, thinner interior of the bauble. The heliosphere will expand dramatically. Cosmic ray levels reaching Earth will drop. The environment around our star will change, but Voyager will not notice. By then, it will be dark and silent. A frozen relic tumbling through space with a golden disk strapped to its side. The stars will shift around it. Constellations that humans named will slowly distort as Voyager's changing position alters the apparent arrangement of nearby stars. Sirius will remain bright. The galactic center will remain in the same general direction. But the familiar patterns of Orion and Cassiopeia and Ursa Major will stretch and warp into shapes no human eye has ever seen. Voyager will drift through these unfamiliar skies, carrying images of skies it left behind. The cosmic microwave background radiation will surround it unchanged. That ancient light from the birth of the universe looks the same from every point in the Milky Way. Voyager would need to travel billions of light years to notice a difference. Dark matter presumably streams through the spacecraft constantly. Trillions of particles per second passing through without interaction, without friction, without acknowledgement. The universe's invisible scaffolding flowing through a tiny machine that cannot detect it. Now, let your breathing slow. Let the distances soften in your mind. 13 billion miles is just a number. What matters is the impulse behind it, the need to reach beyond, the refusal to accept that the edge of what we know is the edge of what exists. Voyager carries that impulse forward, a small machine with a golden heart drifting through the space between stars. The signal still reaches Earth tonight, 160 bits per second, a whisper crossing the void. Scientists listen. They treasure every word. They know the whisper will stop someday soon, but not tonight. Tonight, Voyager still speaks. And somewhere in the data, in the plasma oscillations and cosmic ray counts and magnetic field measurements, the universe speaks back. Close your eyes. Imagine the darkness between stars, not empty, humming, warm in places you would not expect, structured in ways no one predicted, And through that darkness, it's a small golden disc carries the sound of thunder and the laughter of children and a mother's heartbeat toward a future none of us will live to see. That is enough. That has always been enough. Rest now. The stars will keep their watch